so let's make a start. So for those of you who are supposed to be here, where are we in the lecture notes? So we're chapter 4, page 105 on this Gaussian distribution. So we're going to finish chapter 4 today, and that's it, because we've got plenty of time to finish the course, still 7 weeks left, 3 chapters. And so we're going to look at 2 things. One, which is this sheet, so there's about 38 pages here, and this new sheet on IVLE. Why is it so light in here? And this second sheet, which is computing the mean and variance of a Gaussian, so we'll talk about that later. Okay, so basically where have we got to? So we've been talking about random variables which are continuous. And yesterday we finished, we discussed the notion of 2 continuous distributions, which was the uniform distribution, which is basically a kind of block rectangle where basically the probability of any area of equal length of equal probability, and the exponential distribution, which is a kind of type of density used for inter-arrival times. So kind of maybe the most fundamental distribution that you will study if you do statistics or probability any further is this notion of the normal or Gaussian distribution. And for those of you who did mathematics at A level, or the equivalent, you would have seen this notion in probability tables. So what is the normal distribution? Why is it called so? We will talk about that later on. So the notion is you have a random variable x, it's continuous, and it's real valued. So it could potentially take any value on the real line. It could be 10.77, it could be minus 542 or something like that. Okay, and it's a random variable of this type said to have a Gaussian or normal distribution. So the phrase normal and Gaussian is interchangeable. If I say normal, I mean Gaussian. If I say Gaussian, I mean normal. It's the same thing for this course. And if it's a normal or Gaussian probability density function, is a normal distribution if the density function looks like, as you can see labeled here. So this PDF, f sub x of x, is 1 over sigma root 2 pi exponential minus 1 upon 2 sigma squared x minus mu squared for x in the real line. Okay, mu and sigma are parameters. Mu is actually the mean, as we will see later on, and sigma is the standard deviation. Okay, we use this notation n, mu, which is the mean, sigma square, which are the parameters. So mean is a real number between minus infinity and infinity, i.e. has the same support as the associated random variable, and sigma squared, of course, is positive. Sigma is taken to be strictly positive as well. Okay, it's strictly positive. We don't talk about, in this course, Gaussian distributions with 0 variance. Okay, very good. So let's try and understand a little bit about this probability distribution. So it's called the normal distribution because it's a byproduct of something called the central limit theorem. The central limit theorem is something we're going to study later on, so we won't dwell on that. So the central limit theorem basically tells you that this distribution appears very routinely. That's why it's called normal. And Gaussian because of the German mathematician Carl Friedrich Gauss. Okay, so how does this distribution, what does the distribution look like? So it's supposed to have, they say the phrase bell-shaped, but it's not, I don't know of a bell that looks like that, but anyway, basically what it is, so if you take x is equal to mu, that is x is equal to the mean, okay, and here, so obviously the exponent disappears, you get 1 over sigma root 2 pi, okay, so if you optimize this function in x, you will find that x equals mu is its maximal value. Okay, so that's the mode or the highest value of this function as a function of x. Okay, and basically the function at that point, so that's the highest. Here we're taking x is equal to 0 because mu is equal to 0, so that's the highest point. And then because of the nature of the function, it's an even function. Well, it's to say that basically if I take a point here, f of minus x, that's equal to f of x. That's what's called an even function in mathematics. So basically around the mean, mu, the function is symmetric. Okay, so that's why you have this shape which looks like this, and it decays towards 0 exponentially fast. It's never equal to 0, but of course it goes to 0, and the limit as x goes to infinity or minus infinity. Okay. Now the interesting thing about this thing, and we're going to use this fact very frequently, is, for example, if you're interested in computing Gaussian probabilities. So for example, I suppose I want to find the probability that x is bigger than 2. Because of this symmetry of this curve, the probability that x is bigger than 2 is the same as the probability x is less than minus 2. So what I'm trying to say is the area under the curve here and the area under the curve here is identical. Okay, and that's a key point about this probability distribution, as we shall see later on today. Okay, so as I said, the maximum is, you can easily maximize that. The easiest way to maximize that function is you take the natural logarithm of the function and you differentiate with respect to x, set equal to 0 and solve. You'll show you that the maximum is x is equal to mu. You take the second derivative will be negative when x is equal to mu, ergo the point x equal mu is a maximum of the function. Okay, and of course the maximum of the function is then evaluated as 1 over 2 sigma root 2 pi. That's the highest value of the density function. Of course, it's not the probability that x is equal to mu. So the other points, well, as I said, in the limit as x goes to plus or minus infinity, the curve goes to 0 exponentially faster than exponentially because you have a square there. Okay. And indeed, the function is a PDF. Why is it PDF? Because it integrates to 1. Why does it integrate to 1? Well, I could tell you, but we don't do that in the course. Let me just try and tell you why that's equal to 1. Well, basically what you can do in this integral, this is just for those of you who like mathematics. You don't need to know this for the exam or anything. I'm just telling you if you care. What you do with integrals of this type is you make a change of variable. So you make the change of variable u is equal x minus mu over sigma. Now, if you change that variable, what you will get is this same integral, except you'll lose the sigma that comes from the Jacobian transformation, and you'll get e to the minus u squared over 2 dx. Now it happens that the integral between minus infinity and infinity of e to the minus u squared over 2 times 1 over root 2 pi is equal to 1, because basically you can show that the integral between minus infinity and infinity of e to the minus u squared over 2 du is equal to square root of 2 pi. Okay, and how can you do that? What you do is you can show that you consider the square of the integral, you change the polar coordinates, and when you change the polar coordinates, the integral is easy to do. Okay, but you don't need to know that. Okay, so I'm just telling you if you're interested. So it can be shown, and we're going to see it in a moment. I just want to finish these properties. The expectation of x is mu, so the modal value of the PDF is exactly its mean, right? So the mean and the mode of the PDF are the same. Or the mean of the random variable is the same as the mode of the PDF. And the variance is sigma squared. And these two parameters, mu and sigma squared, explicitly control the shape of this probability density function. Okay, so as we know, the modal value, so if I take x is equal to mu, that's the maximal value. So here, if I take a Gaussian, which is normal to 1, then this basically gives me the peak now at 2 instead of 0, which was the case in my previous plot. Okay, so basically that gives you a shift. So if you increase x, it shifts the mode to the right from a given value of the mode. Okay, now that's what the value of the mu does. What does sigma do? Well, basically sigma squared is the variance. Okay, so the variance, remember, is the square of the standard deviation, the standard amount each number deviates from the mean. Okay, so as you increase sigma squared, basically you make the variance larger, so you're going to make the density flatter. So you basically spread out the probability density of the associated PDF. So as you can see here, this is a Gaussian normal norm 1. Now if I increase the variance from 1 to 2, basically you can see that you have a bigger spread. Okay, the modal value has gone down because sigma has gone up, and then basically this is something which has more probability in the tails. Okay, so that's the effect of those two parameters. Okay, and then so we will go just to make property 8. So the standard thing to do with these Gaussian distributions, really for computational point of view, perspective, not that there's really much computational to do with a Gaussian in one dimension, but what you can do is typically, instead of working with a Gaussian distribution of a given mean and variance, mu and sigma squared, you typically standardize the random variable. So that is to say, if I have a random variable x, and that's normal mu sigma squared, and I say z is the random variable x minus mu over sigma, you can show, and we don't do it in this course, unfortunately. I used to do it in mine, but I think it's not so hard to show, really. But anyway, then this associated random variable z, or z, is Gaussian distributed with 0 mean and unit variance. Okay, and then basically this PDF of this is like this: f set of z is e to the minus z squared over 2 times 1 over root 2 pi. Okay, and that's the Gaussian PDF of a standard Gaussian distribution. It's called standard because the mean is 0, the expected value of z is 0, and the variance of this you can also show very simply is 1. Okay, that's why we call it standard Gaussian. And there are a lot of things known about this function and the associated areas under the curve. Okay, let me see if I want to say this yet. Okay, we will talk about this in a moment. Let me just stop this and start doing something which might be of interest or use. So as you note, one of the properties that we said, I've been saying it 2 or 3 times already today, is that the mean of a Gaussian is mu and the variance is the sigma squared, and it's actually not that difficult to show. Okay, so it's not like, you know, it's well beyond your capabilities. It isn't. You can easily do that. You can do that even at A level, actually. You don't even need to be able to be a second year undergraduate or later. So let's just investigate that. I'll show you this. I suspect that no one will ever ask you to do this in an examination, but at least if one day you have to do this for yourself, you have a reference to do that, or someone's taught you how to do that. So let's say, so we have this density function. So this is just a minor modification. So f of x, the PDF, as we said, this is 1 over sigma root 2 pi, exponential minus 1 upon 2 sigma squared, x minus mu squared. X is real valued. Okay, and basically what we want to do is we want to look at the mean of this random variable first. Okay, the mean is not actually that difficult to compute. Okay, so the expectation of x, the mean, so I'm using this e of x notation here, by definition, it's the integral over all possible values of x, so x goes from minus infinity to infinity, of x times the PDF. Okay, that's the definition. Now if you look at this the integral at the top of the page as you see it, it doesn't look very pleasant. But it doesn't look impossible because you have something like roughly x. So if mu and sigma square, if mu is equal to 0 and sigma squared was equal to 1, you'd have something like x e to the minus x squared over 2. And we know how to do that integral because the integral of x e to the minus x squared over 2 is simply minus e to the minus x squared over 2. If you differentiate minus e to the minus x squared over 2, you'll get x e to the minus x squared over 2. So we know how to do that integral. It doesn't look too bad. So what you can do is a substitution, and so that's the trick that we mentioned just a few moments ago. You make the substitution u is equal to x minus mu over sigma. So that's what I'm saying here. You make this substitution. So if you make that substitution, what happens to the integral? Well, first of all, this exponent becomes minus 1 upon 2 sigma squared times z, and z, this thing goes. So x minus mu over squared over sigma squared is exactly z squared, or u squared, sorry. So this becomes e to the minus u squared. 1 over root 2 pi stays. X, well, x is equal to u sigma plus mu. Okay, that's what you get here. And the factor sigma cancels with the sigma here from the change of variable. Okay, so when you change variables, you have this Jacobian which comes in. So that's why you lose this factor sigma. Okay, I'm pretty sure you did integration by substitution A level. Even I did that. And they may have even gotten harder over the years. I don't know. But that's the integral we have left over. Okay, now it's our job to do this one, and it's not too hard actually. So first of all, this is a linear kind of thing, so I can say this is equal to u times this integral times, so I have this thing, u times this, the sigma's a constant, it comes out, and I have mu times this thing, okay? But the integral of this thing is 1, remember, that's what we started this lecture saying. So basically what we're left in over is this integral is precisely sigma plus integral minus infinity to infinity, u times this stuff here plus mu, okay? And now we're almost done, because like I said, the integral of u e to the minus u squared over 2 is known, right? You can compute it. It's minus e to the minus u squared over 2. So this 1 over root 2 pi I've taken out of the integral. Okay, so now the limit is u goes to infinity or minus infinity, while this thing is precisely 0. So the expectation of x is precisely equal to mu. Okay, so here this is an explanation. So this is an explanation of these calculations. This was the substitution here, and this one I've used the fact that this integral is 1. Okay, and I explained how you could do that if you want. I don't see a reason to, I mean, I can do it for you if you want. I'll have to remember my polar coordinates, but it wouldn't be a problem. Okay, so that's the expectation of x, right? It's mu, as I said. That's what we were saying. Now we want to compute the variance. The variance is a little bit more tiresome, but it's still not too difficult. Again, you don't need to worry about these calculations too much because you probably won't be asked to do this. I won't ask you to do this, and I don't think the other 2 lecturers will either in the examination. But you have this as a reference, and also it gives us something to do in the lecture. So in order to compute the variance, that's the expectation of the square of the random variable minus the expectation of the expectation all squared. Okay, so we have the expectation as mu, so we just have to find the second moment. Okay, we know that the variance, well, we've been told that the variance is sigma squared. So what I'm expecting at the end of this calculation is the expectation of x squared is going to be mu squared plus sigma squared. So then mu squared plus sigma squared minus mu squared is sigma squared. Okay, that's what I'm trying to get to. Now the question is how to do the integral. Okay, so now I have the integral between minus and infinity, okay, x squared times the PDF. Okay, so now what am I going to do? Well, I'm going to play my same trick. I make the trick that u is equal x minus mu over sigma. This is the trick that you always do with these type of Gaussian PDFs. So if I do that trick, I get e to the minus u squared over 2, 1 over root 2 pi is still there. The sigma disappears from the change of variable, and x squared is u sigma plus mu all squared. Okay, so that's just the change of variable thing that I did already. Now what do you want to do? So now we'll just do something simple. We'll just multiply out this bracket. So if you multiply out this bracket, I get u squared sigma squared. That's what I get here, and then I have the rest of the integral. Plus mu squared times the integral of this, which is 1, plus 2 sigma mu times u times this thing. Okay, so that's what we're left with. Okay, I've just expanded out the brackets and used the fact that the integral over the support of the random variable is precisely 1. Okay, now to go further, we can use some work we've done already. This thing, if you look at this quantity, this integral on your far right, that's the expectation of a Gaussian random variable of 0 mean. So that's good news because the value of this integral is precisely 0. How do I know that? Well, that's the calculation I did in the previous point again ahead, right? So I already know that the expectation is mu is 0. Okay, so basically this disappears, sigma squared, mu squared goes down here, and now I'm left with the problem of trying to compute this integral. Okay, now how do I do this integral? You're going to do it by integration by parts. So the integration by parts, how do I do that? So this is again, the choice you make is the one function. I take the function, so I'm going to use v and w, so I choose the function v is equal to u, and dw by dx is u e to the minus u square over 2. Why do I do that? Well, I know when I differentiate v, I'll get back 1, and when I integrate back w, I'll get e to the minus u square over 2. Okay, so if I apply my integration by parts formula, this integral here, all it becomes is w, which is u, times the integral of u times e to the minus u square over 2, which is minus e to the minus u square over 2 between minus infinity and infinity. This one doesn't matter, it's going to go to 0. Minus the integral between minus infinity and infinity of the derivative of u, which is 1, times the integral of e to the minus u square over 2 times u, which is minus e to the minus u square over 2. That's why I get the plus there. Okay, and now we're almost done, because as like I say, this one is 0. We know this one is square root of 2 pi. That's what I told you earlier before. So the value of this integral is going to be sigma squared times root 2 pi over root 2 pi plus mu square. Okay, so what does that mean? It means the expected value of x square is equal to mu squared plus sigma squared. So the variance is mu squared plus sigma squared minus mu squared is equal to sigma squared. Okay. Again, this is just a calculation. You can be happy with it. You may not be happy with it. It's okay. We don't have to do this in the exam. I'm just telling you, some of you may be interested. I'm assuming the students who come to this class are actually interested in the class, so I'm trying to tell you things which are useful. Okay, but you're not going to get this in the exam. Okay, so don't feel too worried about it. You probably can do, you should have been able to do this in school, right, if you did A-levels or the equivalent. Okay, so that was just a sidetrack. Let's go back to the lecture notes. So we're talking about this standardization, x minus mu over sigma. Now the reason, and you saw that twice in my integration exercise, right? I did a substitution. U in that case is x minus mu over sigma, and I turned basically my Gaussian with mean mu and variance sigma squared into a Gaussian with mean 0 and variance 1. Now the significance of this thing is basically we know a lot about this function. It's a function that even in the 70s, 60s, 50s, 40s, one could do a lot of things with that. So the importance, and I think it's no longer important anymore, but if anyone anywhere does calculations for statistics on a piece of paper anymore, the fact that they're tabulated is useful. What does it mean, tabulated? Okay, let me explain to you. What it means by tabulation, if we look at the plot of the Gaussian, right, computing the integral under this curve actually is not analytically tractable. There exists no function which we can write down, which we can compute without any loss of precision, which gives us the exact value of the integral. For example, if I integrate the function x, I know the integral is x squared over 2, okay, and I can put in any limits, and so long as those limits are finite, I can evaluate the function, right? The integral of this function, right, you can see if you want to integrate this function between two finite limits is not known, okay? And it's not the first case. You will see many examples if you study probability statistics at any higher level. You'll see many cases of integrals which are not known. So what it means by tabulated is the fact that there exists very precise numerical approximations of areas under this curve. Okay, and these tables represent the associated numerical value of the approximation of these integrals. Okay, this is based on numerical integration methods. It's a kind of whole area in applied mathematics, deterministic numerical integration. Okay, so what it means is that there is a lot of information known about the areas under the curve up to some very, very precise value, which is not the true value, but it's so close that anybody who really cares, no one should care about the discrepancy because it's minimal. So that's what it means by tabulated. Now, of course, tables don't matter anymore because really you just use computer. You'd use a computer. I don't know anyone who does a numerical statistical analysis by calculator anymore. But you can get them in the table. More importantly, there are these approximations. Okay. So then, as we said on the previous slide, and as I've said frequently already today, if you have a Gaussian distribution with the given mean and the given variance, I can always, by change of variable, turn that into a Gaussian distribution with zero mean and unit variance. And so if I want to compute, for example, areas under the curve or probabilities associated to an arbitrary Gaussian distribution, I can simply perform standardization and then consider the associated standard Gaussian random variable. So this is what this point means. Whenever x is normal mu sigma squared, what we do is we just, and we want to compute the probability that capital X lies between two values, little x1 and little x2. That's what I mean here. By using this transformation, I can get at the probability by using the standard Gaussian. Okay, so what does that mean? Well, that means if I'm interested in capital X being between little x1 and little x1 and little x2, now if I subtract mu from all sides of this inequality, I'll go little x1 minus mu, x minus mu, little x2 minus mu. If I divide all the sides by sigma, I'll get x1 minus mu over sigma. Z, which is this thing, is less than this. Okay. Now, so then basically what that means is that the probability that capital X lies in this interval is the same that the probability that Z, the standard Gaussian random variable, lies in this interval, where little z1 is like this and little z2 is like this. Okay, so what it means is I can do calculations with the standard Gaussian instead of this one, and we know a lot about numerical approximations of this quantity. Okay, that's the whole point here. Okay, that's probably why. So if you remember, if those of you who did statistics beforehand, maybe in upper classes at NUS or at school beforehand, they typically use standardized variables, and you look at tables, and this is actually the reason why, if you didn't know beforehand. Okay, very good. So let's see an example of this. So here's an example. So X is Gaussian distributed. It's a mean 50 and standard deviation 10. And I want to compute the probability that X is less than 62 and bigger than 45. Okay, there may be reasons why you want to do that. So what do we do? Well, what we do is with this standardization process. So I've got X, I subtract its mean, which is 50, and I divide by its standard deviation, which is 10, which means this limit becomes 45 minus 50 over 10, and this one becomes 62 minus 50 over 10, which is the probability that Z lies between this interval minus 0.5 and 1.2. Okay? Now you can forget about a lot of this slide because actually I think it's wrong. So this one here is the same as the probability that Z is less than a half and less than minus the probability is less than minus 0.5. Okay, what does this thing mean? What you really want to calculate? So let me just remember 1.2 minus 0.5. So the plot here. So here I've got 1.2, that's the point here. I've got minus 0.5, and I want to compute the shaded region. So in order to do that, I compute the probability I'm less than 1.2, which will give me the entire shaded region here. And to compute the probability I'm less than minus 0.5 is this shaded region here. And if you take the difference, you get the original shaded region. Maybe I'll just draw that on the board. I know that some of you can't see this, but I just want to illustrate what it is that calculation is all about. I'll try and make this as big as I can. Too bad for the people who didn't come to the lecture. You can't see this very well. So the idea is what you want to compute. So I think this is 1.2 and this is minus 0.5. I've already forgotten because I'm getting old. Let me see. Yes. So what we want to do is we want to compute this massive shaded region here, okay? And what we've said, and this is Z, and this is f of Z, and Z is Gaussian normal 0.1. The peak is supposed to be here. You can understand I'm not very good at drawing. So what this line is talking about, so there should be an equal sign here, and you can forget about these numbers. This is not very helpful. I don't know what that does. So what this thing says is you compute. So where's the board rubber? Right here. Okay, so what this thing says is you compute the probability I'm less than Z is 1.5. Okay, so this area here, that corresponds to the probability that Z is less than 1.2. Okay, and so then basically, if I put 0.5 here, this is basically the probability that Z is less than minus 0.5. And this whole thing here is the probability that Z is less than 1.2. And basically what this equation says is to find the original shaded region here, I take this whole region and I remove this part and I'll get this part here. That's what it means just in terms of shaded regions. I know that you're all clever enough to know about integrals, just in case you don't understand the formula. Forget about I don't think these lines are correct, actually. I'd have to check them. I wasn't very happy with them. So now, to get this number, the probability Z is less than 1.2, there's some nice tables which tell you what that number is. There's also some nice tables which tell you that. And so apparently it's 0.5764. Okay, statistical tables. So I'm not very happy about this. I don't like statistical tables because I think you're all too, you don't do these things in anymore, but I'm obliged to tell you about them, so I will. The reason I don't like statistical tables is because, this is a computer age, right? Nobody uses statistical tables. Even when I was at school, you didn't need them. Anyway, so let me just tell you about this. So any introduction 25 years ago for a statistical textbook would tell you about statistical tables. And basically, these are just tabulations of those integrals that I've been talking about. So what they say is, if you well, he doesn't define 5z, so 5z. So 5z, what is it? So first of all, let's define 5z. So 5z is the CDF, cumulative distribution function, for a Gaussian random variable with 0 mean and unit variance. So that's what 5z is. Now what this thing says is that these tables give you values of 5z for given z's. Okay? And 5z is a CDF. They'll either give you this or they'll give you 1 minus 5z. 1 minus 5z is called the survivor function, not that it's important today. Okay, so for example, you will have 5, 1.2, so that the probability that z is less than or equal to 1.2, and that's apparently 0.8849. And all that number 0.8849 is the probability I'm less than or equal to 1.2, and is an approximation of the area under the curve. So in my previous plot, it was just the area to the left of 1.2. Similarly, the probability of 1 minus phi 1.2 is the probability I'm strictly bigger than 1.2. Z is bigger than 1.2 is the area to the right of the point 1.2. Okay, and these are, you can find them in tables. Like I say, these days you actually use the computer. Let's just continue on. So some tables also give the 100 alpha percentage points little z alpha. What does that mean? Let's try and understand it. So there's a lot of words, but basically, if I give me a number alpha, alpha is a number between 0 and 1. Okay, so normally this is going to refer when you do confidence intervals or hypothesis tests, as we will do later on in this course, the level of confidence of the test or whatever like that. So normally we take Z as alpha as a number in 0.05. Now Z alpha are called, typically called quantiles. So if alpha is 0.05, what the table will do is it will tell you the value of little z, which achieves the probability that z is bigger than Z alpha is equal to 0.05. So what does this mean? Let me just try and interpret to you what this formula means. Just again, sorry, I have to use this because I can't do anything else. So you have this Gaussian. This is a Gaussian PDF. This is Z, and this is Fz of Z. I'm sorry that I don't normally try not to do this in these big classes, but there's only 20 of you, so it doesn't matter. Okay, so now this says the probability that Z is bigger than Z alpha. So here what I'm going to try and do is interpret what this thing means. Okay, so basically if I take alpha's 0.05, so here, this area here is 0.05, then what the table is telling you is this value of Z here. So this is called little Z alpha, is a point on the Z axis, Z axis. Okay. So in this case, I think you can just about read it. Basically, 1.645 is the value for which the probability that a Gaussian random variable is bigger than 1.6.45 is 0.05. Okay, that's what it means. That's what it means. Okay, and as I said, because the PDF is symmetric, that's an even function. That's what this means, symmetric, even function. The probability here is identical to here, so if I put minus Z alpha here, that's 0.05. Actually, it's 1 minus 1.645. I'm sure that you remember, if for those of you who did this hypothesis testing, that you'd remember this is minus 1.645. Okay? Well, you don't have to remember, there's no reason to. It's just I've done so many hypothesis tests when I was a student and I remember the numbers. Okay, so that's what this thing is calculating. That's what so this is the whole point of this slide. Hopefully it's clear. All right, very good. Examples using statistical tables. Okay, so we don't have the statistical tables. I was never given them. I'm pretty sure this shouldn't be difficult. If you find that you are not happy with the fact I haven't explained how to use a statistical table, you can send me an email. The first lecture we're back, because we have the recess week or reading week, I will go through it, okay? I'm not doing reading of statistical tables for you guys. You know how to do these things. But if you're not happy, please email me. I'll do it for you. So let's just have a look at this. So X is Gaussian, mean 3, variance 0.5 squared. And we want to find the probability is less than 0.2, 0.3, bigger than 2.5, and it's in this interval 3.54. Okay, so the solution is what? So X, I want to find the probability that X is less than 2.3. So I do my trick, I make it Gaussian, standard Gaussian. So I subtract 3 from 2.3, and I divide it by the standard deviation as 0.5. Okay, so now the random variable x minus mu over sigma is standard normal, so that's why we write z, and that's the probability that 2.3 minus 3 over 0.5 is minus 1.4. So now I want to compute the probability that z is less than minus 1.4, so let's suppose this is minus 1.4. That's the same as computing the probability I'm bigger than 1.4 due to the symmetry of the Gaussian distribution, okay? And the table will tell you the probability that I'm bigger than 1.4 is apparently 0.0808, okay? So similarly, we can do the same thing here. So now I want to find the probability that x is bigger than 2.5. I play the same trick. I subtract the mean and divide by the standard deviation. So this is 2.5 minus 3 over 0.5. 2.5, sorry, minus 3. This one becomes z, again, because I'm standardized the random variable. This number is minus 1. So now I want to compute the probability z is bigger than minus 1. So suppose this point is minus 1, so I'm computing this area. And of course, as by the symmetry, that's 1 minus the probability that I'm less than or equal to 1. Okay? Because basically I say here, and then I go less than or equal to is here, so it's the complement. Oh, sorry, greater than or equal to. What am I writing now? Minus 1. So I was starting here, so I want the probability I'm greater. So I want this area here, this is minus 1 here, and I can do the probability that's here and do this complement. Okay, and again the table. Yes, sorry. You can just Google statistical table for normal Gaussian statistical table. We can do it now, actually. Why don't we do it now, since you've raised the question? Okay. Let's have a look. Maybe I should do this, actually. I just dismiss it because I'm so fundamentally against it. But statistical table. Normal. Okay, good. Okay, here we are. Standard normal turbo. So there's the first hit. There's the second hit. I just wanted to take it like that. There you are. So there you go. So let's see if we can put these two things together, since you've asked. Maybe I should have done this, actually. Okay, so in this example, you have the probability. So in this case, I want probability to the left. So I want, for example, in part A, I want the probability Z is less than minus 1.4. So let's see if the table has that number. Minus 1.4. Table entry for Z is the area under the curve to the left of Z. So minus 1.4 is 0.808. I think this is what point says here, right? 0.0808. Yes, 0.0808. Okay. So that's how you get that number there. I mean, I just Googled, I mean, literally just did it because you asked me. Because this table gives you the area to the left, right? So that's why I have to look at the areas to the left in this example. In this example, the area, I want the probability that Z is bigger than, there's no less than in this one, so it doesn't work. So I would have to work. So now I want the probability Z is bigger than minus 1. Okay, so that's this one. So that's 1 minus the probability I'm less than minus 1, which is this one. So the probability I'm less than minus 1, according to my table, here, sorry, it's 0.1587, so I guess it's around at 0.84 or something, I hope. Yeah, there you go. That's what you get there. Is that clear? Or is it? Yeah, so I don't know which table he's going to give you. Actually, I will ask, because I never did these tables. I just don't think that you should be doing this at this level. Anyway, so then, for example, if I want to compute the probability that x is less than 4 and bigger than 3.5, I subtract 3, I divide by 0.5, that's my favorite thing. So this number is 1 over 0.5 is the probability Z is less than 2, and this is 1, I hope. 1.5, yes, this is 1.5. So this is the probability that Z is less than 2 and bigger than 1. That's the same as the probability Z is less than 2 minus the probability is less than 1. Okay, we should be able to get these numbers from this table. So the probability Z is less than 2. We've got plus 2, we can do 2 here, it should be quite high. So 0.9772. Sorry, this is the wrong one. He doesn't put that there, he's gone the other way around. But this was 0.9772. Probability Z is less than 1 is 0.84, so you're talking about 0.12, something like that. Yeah, 0.135. Okay. Yes? I have no idea. I didn't calculate these numbers. Let me have a look. Let me have a look at the table. Maybe it's just the number of significant figures. So I don't know if it's the same table. I mean, you know the Gaussian, standard Gaussian CDF up to 100 decimal places. So I think once you get to the 5th decimal place, it doesn't matter too much. I think typically if you give an answer up to 3 decimal places at a degree level, that's enough. I mean, I'm not going to dock marks for 4 or 5 decimal places. This becomes silly, I think, in my opinion. And I will definitely not do that. Okay, so yes, as I said, around 1.35, something like that. Very good. Okay, so you can do this in Excel. I would not do this in Excel because I don't use Excel, but you can find many packages which will calculate this. So you can, the one that we use in statistics called R, you can download it for free and it will give you the answers in seconds, for microseconds in fact. So for example, if you suppose that X is Gaussian, mean 50 and variance 102, if you want to find the probability that X is less than 45, you just put in this command, which is norm.dist, 45, which is the point X, 50, which is the mean, standard deviation, which is, it should be 10 squared, I think he's got the mistake. It should be 10 squared, not 10, 102. So this is 10, which is the standard deviation. True, I'm not sure what that means. I guess that's probability. and that gives you the numbers that we were working with there. Like I say, you can use any package you like. MATLAB has these numbers in them, R, and other things. And again, if you want to find, for example, the probability x is less than 62, again, you know how to use a computer at this age. So there you go. And you just calculate that number. Okay. All right, let's finish this part off before we fall asleep. So if you want to find the inverse normal CDF, what does that mean, right? So what that means is I want to find these values, like I was explaining before. So the inverse Gaussian CDF, what it means is kind of finding these values. So I have 0.05, and then I find the z, for which z is bigger than 0.05, or in fact the other way around, less than 0.05. So the inverse CDF is just the inverse. So what does it mean, the inverse? Okay, so the inverse, so what this thing is computing, so you have this, remember this function phi of x, okay, and that's equal to some number, that's in 0, 1. Remember, that's a CDF. This means the interval 0, 1. So this is a number between 0 and 1. So what this thing says, if I take a z, and I take phi inverse of z, then this belongs to a real. So this gives you the real number for which the probability that I'm less than or equal to, this gives you a number, so the probability, so this is the value x, which gives you the probability z, that you're less than or equal to x is z. Okay, so basically what does this mean? So here, I'm trying to write this down properly. Okay, so suppose this value, yes, this number is 0.05, then basically what this function will do is phi inverse of 0.05 will be this point on the z-axis. That's what the inverse CDF does. Okay, so one more time, this is a number in 0, 1. I take the inverse and it gives me this point. So if I take 0.05, it gives me the value of z, which the probability that to the left of it is 0.05. Okay, that's what the inverse CDF does. Okay, more precisely, so this is, for example, if x is normal 74, I think he means 7 squared. He's made the same mistake here. This is 7 squared, not 72. Then normal inverse 0.8874, 7 gives you 82.225. And what that means is the probability that x is less than or equal to 82.225 is 0.88. That's what I was trying to do with this curve here. I was just trying to illustrate it using symbols, but that's if you'd like the same explanation. Okay, and if you want to do this for the standard one, you just do apparently normal dot s dot inv. Okay, that basically means zero mean unit variance. Okay, so we haven't got a lot to do. Maybe we should have our break. We'll have our break now, and then we'll look at these examples. Okay, so we break for 5 minutes. 5 minutes. We resume at 14:48. Thanks. Okay, so let's finish up this chapter. So let's look at some examples associated to this standardization, tabulation, and so on and so forth. So if you're given a common test, the average grade is 74, the standard deviation was 7. If 12% of the class are given A's and the grades are curved to follow a normal curved to follow a normal distribution, what's the lowest possible A and the highest possible B? Okay. Might not be surprised you to hear that this is roughly very much what we do when we get your grades. That's what we're asked to do. So what we want to do is we want to find an x such that the probability that the random variable x, which is associated to the score, which is supposed to be Gaussian, is equal to 0.12. So the probability that x is greater than or equal to x is equal to 0.12 implies that the random variable z, which is a standard Gaussian distribution, i.e. x minus 74 over 7, is bigger than little x minus 74 over 7. Okay, and that's got to equal to 0.12. Now the probability that if you go into the statistical tables, the probability that z is bigger than z is 0.12. So I guess we can go to minus values here. So let's see if we can actually do this. So we look at 0.12. So that's around here. It looks like to me. Is that what it gets here? Should be minus this. Yes, 1.175. Apparently that's what it is. And And so what that means is basically, oh yeah, linear interpolation. I don't know, and I refuse to teach linear interpolation. It's just ridiculous. But anyway, you can obtain this value using a numerical approximation. Okay, and if your z is 1.175, you can just solve z is equal to x minus 74 over 7. If you solve that, that should give you that x is equal to 82.25. So what that means is that the lowest possible a is 83, so I assume you're giving integer values, and the highest possible b is 82. That's really what it means. Okay, is integer scores. So it means that basically 12% of the class are getting A's, and 88% aren't. So I refuse. I'm sorry. If you really want to learn it, I can even read it. So okay. So in this case, what we want to find, example 2, is to find the 60th percentile. So the 60th percentile, what does it mean? Is the value x such the probability I'm less than or equal to x is 0.6. That is what the thing means, the 60th percentile. So now if I standardize that, so the probability that x is less than or x is going to equal 0.6. So I standardize, so I have to do x minus 74 over 7, okay, which still gives you a standard normal random variable where the probability of less than or equal to 0.6 gives you the value of z, and apparently that is if I've got 2.533. Let's see if this is really true. Let's see if I can. 2.533. 2.5. So the probability I'm less than the probability. Oh, sorry, 0.6. Excuse me, I'm looking at the wrong thing. 0.6. It's here. It's around here. So around 0.6 is between 0.2 and 0.3 apparently. Yes, 2.533. Okay, and so then you solve the equation x minus 74 over 7 is 0.2533, and that gives you the value of x, which is apparently 75.77. So what does that represent? It means that basically 60% of the class, at least basically they get 75 marks is the upper, so 60% of the class gets 75 or less essentially. Okay. Let x be the amount of sugar which a filling machine puts into 500-gram packets. The actual amount of sugar filled there's a variation there, okay? And we suppose that the amount filled is actually Gaussian distributed. On average, it's mu, and the variance is 16. So now, if only 2% of the packets contain less than 500 grams of sugar, what must be the mean fill of these packets? Okay, so we're just basically trying to find mu, and mu is such that the following equation holds. So I want to find that the probability that x is less than 500 is equal to 0.202. So this is the 500, this is the 0.02. Okay, so I want to find the mean such that this is the case. Okay, so now if I standardize the random variable x, I subtract mu, which I don't know, and I divide by the standard deviation, as I hoped God it's 4. It is. Okay, so I want to find then mu such that z is less than 500 over mu minus 4 is equal to 0.02, or if you prefer, I can flip the thing, so I can, so I want to be, so if this is 0.02, this area, I flip the other way, so that's the probability that z is bigger than minus 500 minus mu over 4 is 0.02, and z as you have like that. Okay, so then the probability that I'm less than the probability that I'm less than this thing is 0.02. So basically, we've just got to find the entry in this table, I guess, which is 0.02. 0.02. It's around minus 2.85, something like that, apparently. Yeah, or 2.05 apparently. Okay, 2.05 minus 2.05. So if you solve the equation, in this case you get minus mu. You can do it the other way around, so I get minus the other side. So if you rearrange this equation, it gives you that mu must be 508. So basically the mean, on average, this filling mechanism should be putting in around 508.2 grams, so that basically, as it asks, 2%, the mean fill must be to achieve 2% of the packets containing less than 500 grams of sugar. Okay, that's 3. Example 4. So example 4, the breakdown voltage of a randomly chosen diode of a particular type is known to be Gaussian distributed. What is the probability that the diode's breakdown voltage is within 1 standard deviation of its mean value? Okay. Now the nice thing about this question is basically it doesn't matter what the mean and the variance is. You just basically don't need to know either of those things. It's always the same for any Gaussian distributed, as we are going to show. Okay, that's the key point. All right, the solution, you may not know, the point, the reason is an example is you may not know that before we started. Okay, so the probability that x is within standard deviation, the interpretation of that is that the random variable x must be within 1 standard deviation of its mean if it's x is less than or equal to mu plus sigma, but bigger than mu minus sigma. Okay, and that's the only trick. So once you have that, then the game becomes very straightforward. Okay, because as usual, what you're going to do is you standardize. So I subtract mu and divide by sigma, and if I do that, basically this one becomes Gaussian, standard Gaussian, 0 mean unit variance. This one becomes -1, and this becomes 1. And that's the reason why it doesn't matter what the mean of the variance is in this particular example. Okay, so now I want to find the probability that z lies between -1 and 1, and that's 0.6826. Okay, so this is 1, this is -1, this is the area which has been computed from the tables. Okay, so basically the probability within 2 standard deviations, if you do the same calculation, this is -2 and 2, that's 0.95444, 9.544, right? So remember that 1.96 is the 95% confidence interval, so that's why you get this. This is roughly 95%. 3 standard deviations is 0.9974. Okay, so basically, even if the mean was 10 and the variance was 100, or if the mean was -100 and the variance was 2, you would get the same answer. Okay, and it's basically a property of this Gaussian distribution. Okay, let's have a look at example 5. So gauges are used to reject all components in which a certain dimension is not within the specification 1.5 plus or minus d. Okay. It is known that the measurement is Gaussian and the mean is 1.5 and the standard deviation is 0.2. Okay. We want to find d such that the specification covers 95% of the measurements. Okay. So let's try and interpret what this thing is asking us before we do. That's the only question. So what we want to do is we want to find d such that the probability that our random variable x is bigger than 1.5d and bigger than 1.5 minus d. Okay, so this is where this thing comes from. This is the specification, and our Gaussian random variable has this specification. Okay. Not only that, we want to find d such that this is equal to 0.95. Okay, so that's where this 95% comes from. Okay, so what do we do? Okay, so as usual, you subtract the mean and divide by the standard deviation. The mean is 1.5, rather conveniently, so that 1.5 kills this one and this one, and remember the standard deviation is 0.2, so that's where we get this 0.2. Okay, so that means that we want to find d such that we're equal to 0.95. So this one's pretty straightforward because basically d over 0.2 has to equal 1.96, because basically if you put this 1.96 here minus 1.96 here, this tail probability is a 0.025. Okay, so the solution is going to be that d over 0.2 is equal to 1.96. Okay. Right, and there's 1.96 you get from tables, so I was able to memorize that. Okay, so that gives you the d should be 0.392. It's just the only thing to understand here is once you have this statement, then you know you can go to the Gaussian and what standard Gaussian. Once you go to the standard Gaussian, you're just looking at a table. Okay, this is the trick is really to read this question and understand what it means. Other than that, the calculations are nothing beyond what you know how to do already. Okay, so we're almost done for the day. We've just got 7 pages left. We may finish early. I'm sure that'll be good news for you. It'll be good for me. I'm getting tired. What are we going to do in this? The end of the class is really about this particular chapter. So if you cast your minds back to yesterday, You'll remember that what we had was we talked about the Poisson distribution and the binomial distribution. So if you remember the binomial distribution, you have n independent and identically distributed Bernoulli trials, the probability mass, and this basically, the probability mass function gives you the probability of x successes out of those n trials where the success probability is p on each trial. Okay, and remember what we said yesterday is that n is large and p is small, or if p is close to 1, then the probabilities associated to a binomial distribution can be precisely, or relatively precisely approximated by a Poisson. Well, it so happens that in the case where n, the number of data points we're talking about, n, the number of trials in the binomial distribution goes to infinity, but the probability goes to a half, that there exists another approximation one can use, which is the Gaussian. So like I said, these approximations these days are not important for doing probability calculations, but this result is useful for other things that you do in probability theory. So this is why we tell you about them. I think that's why we tell you about them. Okay, so basically the thing is that basically n and p, if n is large, p is close to half, you can use a Gaussian to approximate a binomial. That's the take-home message. We'll say it more formally on the next page. In fact, it so turns out that it's a pretty good approximation, even if n is small and p is not very close to 0 or 1, actually. So it so turns out that there's a good approximation if n times p is bigger than 5, and n times 1 minus p, remember what q was, it's 1 minus p, so n times 1 minus p is bigger than 5 as well. Okay, it's a rule of thumb. That means that it's a reasonable approximation. So if you're asked to approximate a binomial by something, you want to check n times p. So if n times p is like this, you look for the Gaussian, but if n is huge and p is close to 0 or 1, then you look to use the Poisson. Okay, so just to verify this was very nicely tabulated by my colleague. So what does this represent? So these bars, what they are the values of the probability x is equal to x. First, in the first case where you have binomial 15, 0.4. So for example, this bar here is the probability that x is equal to 6 if the number of trials is 15 and the success probability is 0.4. Okay, and overlaid is a Gaussian distribution of a certain type. The exact Gaussian distribution we'll describe in a moment. Similarly, in this second example, okay, here n is not actually very big, is it? But 15 times 0.4 is apparently bigger than 5. I'll have to check that. In the second case, you have a binomial 50, so n is big-ish, but 50 times 0.2 is apparently enough for the Gaussian to be well approximating. So remember that the Gaussian is a continuous distribution. The binomial is a discrete distribution. So it's a kind of funny approximation, right? But still, it tends to be. You can see the shapes look the same, but remember these are the probability that x is equal to x, whereas this is density function doesn't represent the probability that x is equal to x. It's something else. So this is a theorem. So for once, I will not go into the details of it. It's actually not. Again, this one is not so hard to prove. I think we should be able to do this at some stage later. Actually, it's essentially something called the central limit theorem up to some. It's essentially a central limit theorem, actually. And if you study the central limit theorem, you know exactly what this means. And if you haven't, you don't have to worry. We're going to do that later on. So the theorem says if x is binomial, okay, and it has mean np. Remember, the mean of a binomial is np. The variance is n times p times 1 minus p. Then for very large n, x minus np over square root npq is approximately Gaussian, standard Gaussian. This is basically this binomial approximation. It's nothing more than a statement. It's just a version of CLT, central limit theorem. You don't have to understand that yet. I'm going to tell you that later. But if you like, basically this thing is basically Gaussian for large n. Okay. Let's see an example of this. Okay. So let's see an example. Okay, sorry about that. What was I talking about? Yes, so x is binomial. Sorry, x is binomial with n is 15 and success probability 0.4. So we know that the probability of x is 4 is 15 choose 4, 0.4 to the power of 4, 0.6 to the 11. Okay, that's just the formula that we have for the binomial. Okay, and that's apparently 0.12. If we think about the Gaussian approximation, we can consider a random variable y, which is normally distributed. The mean is mu, the variance is sigma squared. The mean is, remember that n times p is the mean in this thing, okay, and the variance is n times p times q, okay. That's basically the variance in that central limit theorem. And so we'll think about this random variable. So n times p is 0.4 times 15, and the variance is 0.4 times 0.6 times 15. So that's the variance. So now if I consider the probability that x is equal to 4, and I don't like this first statement. The probability that x is equal to 4, well, okay, you can say it's equal to the probability that x is less than 4.5 and bigger than 3.5. You would, of course, never need to think about that, but okay. Okay, and then the point is that what you can do is now you try to approximate, you can approximate that upper probability, because we know that x and y are good proxies for each other. Of course, the probability that y equals 4 is 0, so of course we're not going to work with that. So we just look with an interval of 0.5 around the position y. Okay, and now what we do is instead of computing this one, right, well, we know how to compute this one, we just calculated it. What we're trying to do in this example is to understand if this Gaussian approximation is useful or not. Okay, now our Gaussian approximation, so remember y was a Gaussian distribution, its mean is 6 and its variance is 3.6. So if I standardize now y, I take away 6 and I divide by square root of 0.6, then what I would get is that z, which is a Gaussian, which is standard normal, and I want to find the probability that z is between minus 0.79 and minus 1.32. Okay, this is of course the probability that z is between 0.7 is bigger than 0.79 minus the probability z is bigger than 1.32, and if you get these numbers from the tables, apparently the value is 0.1214. Okay, so what does this example illustrate? Well, the true probability was 0.1268. We know the answer, and our approximation is 0.1214. So of course it's not the same value because it's an approximation, but it's not too bad. Of course, this is an example. We would never use the normal approximation. There's no reason to. We're just trying to verify whether or not this approximation is reasonable or not. Okay, right. So basically, don't worry, we've only got 2 slides left. So this one looks like a lot of horrible things. This is called continuity correction. So this is roughly what we were doing on the previous slide. So in this above calculation, or the previous calculation, so what do I mean by that? What does my colleague mean? He means basically this thing. Where do the numbers 4.5, 3.5, what are we doing? This is called a continuity correction. So basically what we do is if we want to approximate the value that approximate the probability x is equal k, then what we do is we consider the probability that x is within the interval k plus or minus a half. Okay? And if I want to approximate the probability x is less than or equal to less than or equal to b and bigger than a, or greater than or equal to, I use this approximation here. So the basic things are, when I did this less than or equal to, I'd be less than b plus a half, and I have greater than or equal to, I'd be a minus a half. But now if I change the inequality from greater than or equal to greater than, so the strict inequality, I change from minus to plus. These are just the conventions we use. Okay, this is nothing more than that. Okay, and there are a variety of them. I could read them out for you, but I don't feel like it, to be honest. Sorry. Okay, let's have a look at some examples to finish off. So this is the only example. Actually, it's quite informative, this one. So we have a system. It's made up of 100 components, and each of which has a reliability equal to 0.9. So these components independently function of each other. Okay, basically we're working up for a binomial thing. And the entire system functions when only at least 80 components function. And we want to find the probability that the system functions. Okay, so we can answer this very, very neatly in the following way. So suppose x is the number of components functioning. Okay, so now we know, how do we know? So we know the following, right? So we have 100 components. This is the chance that they're reliable, and these functions are independent. Okay, so whether they function or not is a Bernoulli trial. If they function, 1, success. If they don't function, 0. The chance that they function is 0.9, and they do these things independent. This is a characterization of a binomial experiment. There's 100 independent and identically distributed Bernoulli trials. So this is why here. So here this is not an assumption. So remember in some of the examples we spoke about yesterday and in the past, we have to make an assumption. Here it's kind of explicit in the formulation of the question. Okay, so what are we going to do now? So what we want to do to calculate, so remember that what we want to calculate, we don't want to calculate the probability that the system functions. So basically we want to compute the probability that x is less than or equal to 80. Okay. Now, actually, of course, you can calculate this very fast on a computer these days, but if you prefer, you can use a binomial approximation, which if you have to do calculations by hand, which you don't anymore, but you may have to do in the exam, you can use the Gaussian. So remember that in this case, the binomial has mean n times p, which is 100 times 0.9. So it's 90, and the variance is 100 times n times 1 minus n times p times 1 minus p, which is 9. Okay, so now remember that the Gaussian approximation, if you just go back, the Gaussian approximation, what we've been talking about is this: the mean is np and the variance is npq. Okay, so basically now what we do is we want to compute the probability that x is between 100 and 80. Okay, sorry, the probability that x is functioning when at least 80. So the probability that x is greater than or equal to 80, not less than, sorry. So the probability that x is less than or equal to 80, less than or equal to 100 and bigger than or equal to 80. So I standardize. Okay, so if I standardize, I do x minus 90 over the standard deviation. Okay, which is like that. And now basically what we do is we approximate this thing with our Gaussian. So basically remember this is the probability. So this thing is roughly, so remember this is 79.5 minus 90 over 3, which should be hopefully minus 3.5, and 10.5 over 3, which is this one's 3.5. Right. So this is the probability that this random variable is very roughly equal to that. That's the normal approximation part. So the probability that z is between 3.5 and minus 3.5. This is equal. This is roughly equal to this probability is equal to this. By the way, there's no approximate. This is not an approximation. It's a typo. Okay, so the probability that we want is equal to this. The probability we want is roughly equal to this, thanks to our Gaussian approximation. And this one is exact. So the probability in less than 3.5 and less than minus 3.5 from the tables is very high. Basically, 3.5 is here and minus 3.5 is here. So this probability in the middle is huge, and it's almost 1. Okay, so the chance that this system functions is 0.995. Of course, if I wanted to do this using the exact calculation, I'd have to compute the sum from x is equal to 80 up to 100 of 100 choose x, 0.9 to the x, 0.1, sorry, to the power 100 minus x. You can calculate it, there's no problem with that, but only using a computer. I wouldn't do that using a calculator. Okay, so that's that. I mean, I don't see the point of starting chapter 5 today, because we're going to have a week off, and then after that week, we will have all forgotten what we were doing. So it's better to start chapter 5 in a week's time. The only other thing that I have to say before we conclude is, if you have things that you are not happy with yet at the moment, we've covered 4 chapters. If there's something that you're not happy with, it's not unclear, please let me know, because I've got time to prepare some new notes and go back to them at the end. Okay, so keep that in mind. If you're unhappy, you don't understand something, there's not a formula, there's a concept which is unclear, let me know, send me an email. I'll have time to write some new notes, and I'll put them at the end of the lecture course. Okay, so thanks very much for attention, and I'll see you on the 7th of March. Thanks for the attention.